Good morning, class. Here's chapter 2 review, limits and derivatives. In this chapter, we are going to cover the tangent and velocity problems, the limit of a function, calculating limits using the limit laws, the precise definition, continuity, limits at infinity, horizontal asymptotes, derivatives and rates of change, the derivatives as a function. And at the bottom of the page, you see the definition of a one-sided limit, the limit of f of x as x approaches a from the right. This is read a from the right, equals the limit of f of x as x approaches a from the left. This means from the left, equals L. If both are equal, the limit does exist and it's equal to L. So that's a one-sided limit. So let's get started. Here's the synopsis of what happens with the limits. Number one, here's how we read this. The limit of f of x as x approaches a equals L. And as mentioned before, one-sided limits. The limit of f of x as x approaches a from the left. Here's the limit of f of x as x approaches a from the right. If the two are identical, the limit exists. Here's the definition of a VA, vertical asymptote, has the equation x equals a. If you take a limit of f of x, you end up with either infinity or negative infinity as long as x approaches a from the left, or a from the right. Let's look at all of these graphs. We are interested in finding the limit of f of x as x approaches a. Here's a, so we're coming from the left and the right of a. So let me show you the other pages, the other formation also. So what's happening? Here's from the left side. Of a, that means we are moving this way, this way, this way, and this way. So as we move from the left of a, we are in this branch, we are moving towards this point, we never get there, and the limit is L. All of these cases are the same. And it's important to understand in this case, there's a hole here, there's a solid point here, there's a hole here, there is no solid point, which means in this case, it's not defined at that point, but f of a has a different value, which means we never get to a. That's the concept of a limit. So we don't worry about the limit. The limit works out, it's still L. From the right side, you're moving this side, this side, this side, which means this part, this part, this part, going this way, in all cases. From the left, we are in this branch, and we moving towards this point, having L as the answer. From the right side, we are in this branch, this portion, coming down, and in both cases, we are moving towards L. So what's the difference? If the limit of f of x as x approaches a is L in all cases, the difference is, in this case, f of a is also equal to L. In this case, f of a is not equal to L, but the solid point has a different y coordinate, namely b, and in this case, f of a, we don't have any solid point, and we don't know the answer. But in each case, the limit of f of x as x approaches a equals L. So what does it mean? It means in these two cases, the function is discontinuous at a, but in this case, the function is continuous at a. According to the definition of a continuity, the limit of f of x when x approaches a equals f of a, which is the case here. So all of them are discontinuous at a except this one. However, the limit exists in all cases. We also have a definition of a HA, horizontal asymptote, gives us the equation y equals L as long as the limit of the function when x approaches either negative or positive infinity is L. All right, finding limits by numerical and graphical method, also algebraic or analytical method I'm going to look at. So first we can sort of look at this, and we are looking at the limit as x approaches number 1. And if we plug in, more importantly, the denominator becomes 0, which makes it undefined. However, we will get to the concept a little bit more with more details later on. It's indeterminate form because 0 over 0. So the numerical method says, let's pick values close to 1 and evaluate it. So we're going to go on the left side, pick up values such as 0.5, 0.9, 0.99, so forth, and plug it into this. So here's the evaluation. When x is less than 1, for example, plug in 0.5 into this, it gives you this answer. 0.9 gives you this. And as you add to the number of 9s, it gets closer and closer to 1. But it is important to understand this means we never get to 1. From the right side of 1, 1.5, 1.1, 1.01, so on and so forth. And as you can see, this is the closest one, and this is the answer we plugged in to this function of x minus 1 over x squared minus 1. Now, when we compare these two, there seems to be the limit exists and it's equal to 0.5 or 1/2. However, if that's not good enough, you can make it closer by picking up more 9s over here, by picking up more 0s after the decimal before you get to 1. And then you'll see the answer is 0.5. If we were to graph this, x is approaching 1 from the left, x is approaching 1 from the right. And if we graph this very carefully, it gives us this function. As you can see, there's a hole here because it is undefined at x equals 1, but in both cases, both sides, moving towards the hole, which has a y coordinate of 0.5, because the limit refers to the value of a y coordinate. However, the solid way to prove that, and this is perfect, it's algebraic method or analytic method, by which case we use our algebraic technique. Notice if we plug in, we get 0 over 0. And the technique is factoring. As you see, the bottom is a squared minus b squared. And it factors into a minus b, a plus b. Therefore, we can drop the x minus 1. We get 1 over x plus 1. Take a limit as x approaches 1. And now if you replace it, you get 1/2. All right, using limit laws, if the limit of f of x as x approaches a and the limit of g of x as x approaches a are given, the limit of the sum is the sum of the limits. The limit of the difference is the difference of limits. The limit of a constant times the function, the constant can come out. The limit of the product is the product of the limits. The limit of the ratio or the quotient is the quotient of the limits. Of course, as always, the denominator can't be 0. This concept of a direct substitution, a continuous function at a has the following limit value, limit of f of x as x approaches a equals f of a. Therefore, we go with direct substitution. Functions with the direct substitution property are called continuous at a. And the squeeze theorem, here's the synopsis of the information. If g of x is between f and h of x, so f of x is less than or equal to g of x, less than or equal to h of x. When x is near a, except possibly at a. In other words, we don't care what happens at a. That's the concept of a limit. But rather near a, this is the case. Now the left side, the limit of f of x as x approaches a, and the right side, the limit of h of x as x approaches a is exists and it's equal to L. Then by the squeeze theorem, the piece in between g of x also has the same limit as x approaches a. That's called the squeeze theorem. We're going to put it to good use later on. One-sided limit has already been discussed, and in short, the limit of f of x as x approaches a equals L as long as the limit as x approaches a from the left and a from the right are identical. All right, given the graph, we want to find the limit of f of x as x approaches 2, in which case we are going to look at a one-sided limit. So we're going to look at the 2 from the left and 2 from the right. Please understand, examples of 2 from the left is like 1.9, 1.9999, very close to 2. Examples of 2 from the right is like 2.1 or 2.00001, very close to 2, but from the right. In other words, 2 from the left doesn't mean negative. So 2 from the left means going this way, means going this way. And therefore, we are moving towards this point, which has the y coordinate equal to 3. So that's the answer. So that's the first point. From the right side of 2, we are going this way. So that means we are going this way. And therefore, we are moving towards this hole in a limiting factor. Remember, in a limiting sense, meaning we never get there. So what is the y coordinate of this point is 1. Are they identical? No. Therefore, limit of f of x as x approaches to dne does not exist. Let's look at f of 2. Now, what is the meaning of this solid point? The solid point means f of 2 has the y coordinate that you see here, which is 3. And by the way, because the two are the same, again, the limit doesn't exist. The function is discontinuous at 2, but you can say it's continuous at 2 from the left. What is the limit of f of x as x approaches 4? Or we're going this way from the left side, this way from the right side. And in both cases, coming from the left, we are moving towards this hole. Coming from the right, we are moving towards the same hole, in which case the answer is 4. So the limit does exist. But what is f of 4? When I look at 4, I don't see any, and therefore it's undefined. I need a solid point, and it makes it discontinuous at that point. A concept that is coming up later on. We have the graph, and we are interested in finding the limit of r of x as x approaches 2. We look at the graph to make a decision. Here's number 2. From the left of number 2, it's going down to negative infinity. From the right also. And so the answer is negative infinity. So in both cases, we are going down to negative infinity. In the case of number 5, left side blows up to infinity, right side the same thing. So this limit is infinity. However, as we approach negative 3, whether we approach it from the left side or right side makes a difference. So the limit of r of x as x approaches negative 3 from the left, it's negative infinity, and negative 3 from the right is positive infinity. And that helps us answer VA, vertical asymptotes. By definition of vertical asymptotes, this says x equals 2. This one says x equals 5, and both of these x equals negative 3. Those are the vertical asymptotes. Vertical asymptotes, and those are the equations. How do we find the limits? To find the limit, just plug in and observe. So when we plug in, what happens? The limit of a function as x approaches some number is a number. If it gives you some value, 1, 5, 10, minus 8, you're done. Case number 2. It gives you 0 over a number. When we say 0 over a number, that means 0 over something other than 0. That means it's 0. If it gives you a number over zero, we've seen a number over zero, we used to say it's undefined, but the bottom line is it either approaches infinity or negative infinity. And there's a way we can figure it out. But a number over zero is not undefined anymore in calculus. It becomes either infinity or negative infinity. Indeterminate form is what we come across more often than not in calculus. If you're taking the limit as x approaches, whatever the case might be, 0 over 0, infinity over infinity, infinity minus infinity, 1 to the power of infinity, 0 to the power of infinity, infinity to the power of 0. There are other forms, but these are basically the forms we're going to get started for now. There are many different forms of indeterminate forms. That means we have to use our algebraic technique to figure out what to do. So I'm going to call this more work. And that's what we end up with almost always in calculus. Almost. So first plug in and observe, and it gives us one of those cases. We work them out. So let's do that. What happens in this case? We are looking at the limit of the square root of x plus 4 minus 2 over x. If we replace the x with 0, this becomes square root of 4, which is 2 minus 2, and that's 0 over 0, which is indeterminate, which means we have to do some sort of an algebraic technique to fix the problem. So what is the technique in this case? Anytime we have a square root, we use what's called a conjugate. So we change this to a plus, we multiply and divide by it because it's 0 over 0. Square root of x plus 4 minus 2, we multiply by square root of x plus 4 plus 2 because the conjugate for a minus b, as you recall from algebra, is a plus b, in which case the answer is a squared minus b squared. Therefore, this gets squared up and comes out as x plus 4 minus 2 squared is 4. 4 and negative 4 cancel each other. By the way, before we move on, it's very important to understand the 0 that creates a problem is the 0 in the denominator, not in the numerator. So we are hoping for this to go away. Because of that, when you get to this point, you never, ever do anything. You keep this as a product because you're hoping that the x goes away. So take a look. We didn't distribute. And so what happens now? This x cancels out this x, and the numerator changes to 1. If we plug in, we get square root of 4, which is 2. 2 and 2 is 4. The final answer is 1/4. And we are done. That was an indeterminate form, everybody. All right. Whether we approach -3 from the right or -3 from the left, when you add it to 2, the numerator becomes -1 in both cases. Let me write this. So this is -1 and this is 0. This is -1, this is 0. But I want to explain with a little bit more details as follows. So in both cases, we end up with -1 over 0. However, it really makes no difference for the top. whether -3 approaches from the right or left, because -3 from the right, and I want to pick up an example of that. When we say from the right, that means like -2.9999. And so when you add it to this one, it becomes like -0.99999. Whereas here, -3 from the left is like -3.0001. When you add it, it becomes -1.001. So the numerators are both very close to -1. If you pick any number class, the right side and the left side have the same sign, meaning a positive number, both sides is always positive. A negative number, both sides are always negative. However, the only number that makes a difference is 0. 0 on the right side is positive, on the left side of 0 is negative. So that's where it makes a difference. And we are going to work on this as follows. If I look at this one, it makes no difference for the numerator, but it makes a difference for the denominator. So I'm going to pick an example, -3 from the right, like -2.9, and I add it to 3, and it gives me +0.1. And so we write this as -1/0 from the right. We know any number over 0, it ends up being infinity, okay? However, the sign, as you can see, negative over positive is -infinity. And that's really the key that I want everybody to pay attention to. So, but before we do that, I want to make sure we understand what happens here. And here, let me, over here, -3 from the left. Again, for the top makes no difference. For the bottom, example of that would be -3.1 plus 3, which makes it -0.1. So you have -1 again, but over what? 0 from the left. So what is the difference? The difference is this gives you -infinity, because negative over positive is negative. But this one gives you +infinity, because negative over negative is positive. And that's how I come up with the precise answer, whether it's positive or negative infinity. So I'm going to quickly recap. When I come across a case like this, where the numerator ends up being some number, it doesn't matter, positive or negative. And for that, it doesn't matter, you go from the left to right. When the denominator becomes 0, that makes a difference whether that 0 is from the right or left. And I figure out the sign of that by literally picking up a number, -3 from the right. An example of that is -2.9. This makes it positive. This one, -3.1, because -3 from the left, and it makes it negative. So I have the sign. All right, if we plug in fact, for both cases, we get 0 over 0. And we need to use a technique. The technique for part A rational function is factoring. Now, something that helps is the following. Since the denominator becomes 0, because the denominator becomes 0, and x is approaching 4, then most likely we should have a factor of x minus 4 in the denominator. If x is approaching 5, the factor of x minus 5. Let's say x approaches 5, we should have a factor of x minus 5. Most likely. If x approaches minus 4, then most likely we have a factor of x plus 4. So that should also help you with factoring. Needless to say, the numerator is a piece of cake. You simply take the x out. And so I'm assuming we are okay with the factoring. The factoring is fairly simple. And so what happens is that x minus 4 from the bottom, x minus 4 from the top, they cancel each other. And now, if we plug in, the top becomes 4, the bottom becomes a 5, we are done. Same thing happens with part B. We get 0 over 0, just like part A. So we have an indeterminate form, and it requires algebraic technique. Anytime we have a square root, the technique is to use a conjugate, which means the conjugate of this expression, you just change this to whatever the sign is. If it's negative, make it positive. If it's positive, make it negative. You multiply and divide by that. Again, what is important here is to know that this fraction is equal to 1, because you can't just multiply by any fraction you feel like it. It's important to do it accordingly. And so what happens again to the denominator? Nothing, because remember, h is approaching 0. The denominator, the 0 in the denominator is the one which is giving us a hard time we want to get rid of. So we keep it as a product. However, the numerator is a minus b, a plus b. This gets squared up. So let me just write at the top of it in case. So the numerator becomes the square root of 1 plus h squared minus 1 squared, and we get the following. Again, what happens to the denominator? Absolutely nothing. You notice 1 and negative 1 cancel each other. So we are left with h in the numerator. We drop the h in the denominator, and the numerator changes to 1. Replace the h, and the denominator becomes 1 plus 1 equals 2, and the result is 1/2. 1/2 is the answer. All right. Remember what we do first. First, we plug in and observe. So in the case of part A, what happens when we plug in here? I hope you realize this goes to 0, this goes to 3. So the numerator is 3. What happens when you put it here? 36 minus 7 times 6 minus 42 plus 12. So we plug in to see what we get. Now, the numerator is, of course, 3. When you add up the denominator, 36 minus 42 plus 12, you end up with 6, and the ratio is therefore 1/2. We didn't have to multiply by the conjugate because it ended up being some number. In this case, 1/2. Part B, if you plug in, I hope you realize if you plug in 3, you end up with 0 in the numerator because 1/3 minus 1/3 is 0, and the denominator is 3 minus 3. So you are dealing with a complex fraction. The technique is LCD, the least common denominator, which means what? You look at the numerator, we have 1 and 2 fractions, no more. So for those 2 fractions, we come up with the LCD. If we have more fractions, let's say we have 2 more in the denominator, total of 4, then you come up with LCD for a total of 4. In this case, the LCD is 3x. So you multiply everything, the top as well as the bottom, by 3x. And notice again, this is equal to 1. So it is justifiable. If you multiply it by the first piece, you get x minus these 2, 3, and the denominator, you just write it as a product. You don't do anything. Again, x is approaching 3, that's a problem. So just write this as the product. And so what happens is that, again, remember, x is approaching 3, x minus 3 is 0. You're hoping to get rid of that because the 0 in the denominator is the one that is creating a problem. And so you have the limit of 1 over 3x as x approaches 3. And now when you replace it, you get 1 over 9. We want to evaluate the following limit if they exist, and we want to pay close attention to the graph. We want to be very careful with that. So F is the red function, G is the blue function. We are interested in finding this limit. So let's cut them into 2 pieces. That's really the concept known as limit law. So this one plus this one, and this one, the 5 comes out. So the first thing is we use this one, which is known as the limit laws. The limit of f of x as x approaches -2 plus 5 limit of g of x as x approaches -2. So what is this equal to? We go to the red graph. X is approaching -2. So locate -2 here. So -2 from the left of it this way. We're moving towards this hole. From the right side of -2, we're moving towards the same hole. And this hole has a y coordinate, which is 1. For g of x, the blue function, as we approach -2 from the left and -2 from the right, in both cases, we are moving towards this point, and this point has a y coordinate, which is -1. So a quick recap for the red graph, -2, we are going this way and this way. For the blue one, we are going this way and this way. And they both have a limit. So you plug in 1 here, plus 5 times -1, the result is negative. We want to find this limit. We do the limit laws. Again, we separate them into two pieces. The limit of f of x as x approaches 1 times the limit of g of x as x approaches 1. And we can look at it two different ways to come up with the answer. One way is to calculate each piece, and let's do that. What is the limit of f of x as x approaches 1? Here's number 1. So from the left and right, okay, from the left and right, then I'm going to use an arrow. From the left and right, we are moving towards this point, and this point has a y coordinate. For the blue function, the left side of 1 takes us here, which has a y coordinate -2. The right side of 1 takes us towards this point that has a different y coordinate, -1. So this limit doesn't exist because of that. So I want to make sure we understand this by looking at, so for the blue function, for the red function, we are going this way. For the blue function, we are going that way. Therefore, for the red function, both sides ends up here having the same y coordinate, namely 2. But for the blue one, the left side takes us here. Y coordinate is -2. From the right side takes us towards this point again. That has -1 as the answer. Therefore, the limit doesn't exist. You could also, so therefore, because of this limit doesn't exist. Okay, one of them fails, the product fails. For this, we can do a second method, meaning we look at the product and the limit as x approaches 1 from the left and then 1 from the right. So 1 from the left for f of x, left and right makes no difference. So left and right is the same for f of x is 2. For g of x from the left is -2. So 2 times -2 gives us -4. From the right, limit of f of x, g of x as x approaches 1 from the right. Again, this thing is the same as this one. This was 2, this is 2 also. But the g, when we approach it from the right, has a different value. So 2 times -1 and -2 and -4 are not the same. So that's the second method that shows this limit does not exist. What about the limit of f of x over g of x as x approaches 2? Well, this one does not exist either. Why is that? Because let's look at each case. If you look at the f function, the blue function, as x approaches 2, here's number 2. And it does have an answer over here, whatever this number is, maybe 1.5. And as far as the g of x is concerned, from the left and right, I hope you realize it takes us here, having the y coordinate 0, we can't divide by 0. The denominator approaches 0, while the numerator approaches non-zero numbers. So in essence, you could write the following. So this is becoming the limit of the top as x approaches 2 over the limit of the bottom as x approaches 2. The numerator is close to 1.5 and the denominator is 0. That's why they say it doesn't exist. All right. If g of x is between these two, between the function 2x and x to the power of 4 minus x squared plus 2, in other words, 2x is less than or equal to g of x, less than or equal to x to the power of 4 minus x squared plus 2, for all x, we want to find the limit of this function g of x as x approaches 1. Recall, the squeeze theorem says if f of x is less than g of x less than h of x, when x is near a except possibly at a, and the limit of f of x as x approaches a is the same as limit of h of x as x approaches a, and they are both equal to some value, let's say L, then the middle function has the same limit. The limit of g of x as x approaches a equals L. Therefore, we are going to look at the limit of the left side, 2x, as x approaches 1. And as you can see, it's 2 times 1 or 2. We are going to look at the limit of the right side, this function, as x approaches 1. So now if you plug in, you get 1 to the power of 4 minus 1 squared. They cancel each other, plus 2. So the answer is 2. Since this is equal to 2, this is equal to 2, then the limit of g of x as x approaches 1 is equal to 2 by what? By the squeeze theorem. I can't emphasize this enough. You can't just write this is the case without writing by which theorem. It's called the squeeze theorem, and it's important to make a note of it, by the squeeze theorem. Prove that this limit equal to 0. The limit of square root of x, brackets 1 plus sine squared 2 pi over x as x approaches 0 from the right. We want to prove this. And this requires some prior knowledge of trigonometry and information about the squeeze theorem. So in this case, we should be creative. So here's how it works. We know that sine is between -1 and 1. In fact, let me not use an x, let me use an alpha. We know sine is always between -1 and 1. In other words, that's the range. So the same thing for whatever the argument of sine is. In this case, this argument is alpha. So sine of 2 pi over x is also between -1 and 1. So this is by the fact that the range for sine is between -1 and 1. So we are going to manipulate this to get to this expression, everybody. That's the technique in this case, using the squeeze theorem. So first, we need to square this. So if we square this one, class, if we square this one may think that we're going to square this one too. That's not the case. If a number is between -1 and 1, when you square it, this one actually goes to 0. Here's the reason you square it. So this becomes 1 squared and it's 1, but any negative number when you square becomes positive. So it can be 0, yes, because if it gets closer and closer to 0 is 0. So I want you to see this transition. If I had negative 5, still would be 0 here, because when you square any number, changes from negative, if it's negative, to positive. So we got this expression. All right, look at the brackets. What is missing? Number 1. Well, we have this inequality. We're going to add number 1 to both sides. If I add number 1 to both sides, this becomes 1, this becomes what we are looking for, and this becomes 2. We go back to this expression. What is missing? Square root of x. So if I multiply all sides by square root of x, and by the way, can I do that? Remember, in the case of inequality, when you multiply by a negative number, it flips over. And so we know this is positive. X is approaching 0 from the right. Square root of x is always positive. You multiply this one by square root of x, you get square root of x. You multiply this one by square root of x, you get 2 square root of x. And when you multiply the middle piece by square root of x, you get the whole expression you're looking for. So square root of x times that expression now. Let's take a look at this quiz theorem. If f of x is less than or equal to g of x less than equal to h of x, and we have a situation like that, then the limit of the left side, the limit of this one, and the limit of the right side are the same, then the limit of the middle term is the same also. So let's look at the limit of this one. What do we want? As x approaches 0 from the right, if you take this limit as x approaches 0 from the right, I hope you realize you get 0. Same thing here. So the limit of square root of x as x approaches 0 from the right, this one is 0. The right side, the limit of 2 square root of x as x approaches 0 from the right is 0. Therefore, this expression, square root of x was missing, I put it there. So this expression, the limit of this expression, which is exactly this one as x approaches 0 from the right, is also 0 by what? By this squeeze theorem. That's important to write. I can't emphasize this enough. We have to write this. So let's quickly recap. The technique was to know this property and then working on this to get to this expression. Because sine alpha is between -1 and 1. Alpha can be anything, for example, 2 pi over x. Makes no difference. When you square it, you square this number, whatever it is, 1 is 1, 5 is 25, you name it, but -1, you change it to 0, always. Any negative value, you change it to 0. Since you want this expression, you're going to add 1 to all sides. Since you want this expression, you're going to multiply by square root of x, which is a positive value, all sides. Now, the left and the right, the limits are 0 as x approaches 0 from the right. And the middle term by the squeeze theorem gives you the same result. You want to find this limit. we are going to go to one-sided limit, reminding everybody of one-sided limit. The limit of f of x as x approaches a from the right is L. The limit of f of x as x approaches a from the left is L. Therefore, the limit does exist as x approaches a, and it's equal to L. So let's look at this limit from the left of -6. Let's see what happens to this expression. When we have absolute value of x, it's x if x is larger than or equal to 0 minus x if x is less than 0. So absolute value of x plus 6 becomes x plus 6 if x is larger than or equal to -6, and it's negative of that if x is less than -6. So since this is the case here, this absolute value drops and it becomes negative times x plus 6. In the meantime, we factor out the 2 from the numerator to make our life easy. Therefore, we can simplify this into -2 So the limit of -2 as x approaches -6, and it becomes -2. We're going to take the limit as x approaches -6 from the right. And so what happens is that we can drop this and change it to x plus 6. And obviously the top, we factor out the 2. And the limit of 2 as x approaches any number is 2. Are they the same? No. Therefore, the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches -6 does not exist. A different approach would be to simplify the expression beforehand and write this 2x plus 12 over absolute value of x plus 6 with this means it's equal to 2 if x is larger than or equal to -6, and -2 if x is less than -6, in which case the limit from the right is 2, from the left is -2, and therefore the limit does not exist. That's how we get to the answer.